this computer. All right, I think that we're ready to go here. All right, Gen Chem class, welcome back from spring break. We are going to continue in chapter 17 today. But as we get started, I just wanted to show you, these are the, let me just check something out here before we go too much further. Make sure that we're, okay, I think we're good. All right, just checking to make sure that we're getting the screen in. The exam grades for exam 2 were pretty high. The average was around 84, so I will not, it's actually a little higher than our normalization scale, so I will not be normalizing these numbers. But just to give you an idea that a lot of people scored 80 and above. I believe the top score was 99. All right, as far as announcements go, yeah, the only thing here that really matters is chapter 17B for Alex is due on Saturday. So we're going to be finishing up the rest of chapter 17. We're going to spend today, Wednesday, and Friday talking about acids and bases. But of course, we have some despair to go through. It's amazing how much easier it is for a team to work together when no one has any idea where they're going. He who chases rainbows may eventually catch tornadoes. My reality isn't getting any better, but my fantasies are improving all the time. Unicorns and rainbows, how about that? If things don't improve soon, we may have to ask you to stop helping us. When you earnestly believe you can compensate for a lack of skill by doubling your efforts, there's no end to what you can't do. The mark of the leader is the ability to make decisions. The mark of the survivor is knowing when not to. And finally, it takes 43 muscles to frown and 17 to smile, but it doesn't take any to just sit there with a dumb look on your face. That's one of my favorites. All right, so here we go, chapter 17, acids and bases. So if you recall, let me back up. Some things I expect you to know. From before spring break, we talked about strong acids and bases, weak acids and bases. And we had a slide like this that was similar for acids. We have strong acids, how strong acids behave, total dissociation, no equilibrium, and how weak bases behave. What we're calling here a base is the traditional Bronsted definition of bases, which is a hydrogen ion acceptor. But here we have a hydroxide. This would typically be sodium or potassium hydroxide that goes, we're left with the conjugate acid, base, conjugate acid, base, conjugate acid. So here we have the typical Bronsted weak base definition, a hydrogen ion acceptor, and we're left with OH. This is the equilibrium constant expression for a weak base. So there are two weak reactions that you have to know. You have to know a weak acid plus water and a weak base plus water. This is the other one that we have. The key to all of these problems is knowing what you've got in your system. Once you know exactly what you have, then you can make decisions on where to go with it. So let's start here. Here we are going to talk about a 0.3 molar solution. Actually, what we're going to do is finish up the last two problems on worksheet 14. I know you've already submitted it. I think you've already submitted it, but if not, well, whatever. I can't remember where we stand because that was way before spring break. Let's start here. On the worksheet, we used 0.075 instead of 0.30. So here I'm just going to leave the slide the way it is. We're going to not use this number. We'll use 0.0750. What are the major species? Write the reaction. Ammonia, the classic weak base. H3 plus H2O goes to NH4 plus. Base, conjugate acid. And we're left with that. All right. What are the major species? Well, the major species, to answer that question, we have to know this. This is an equilibrium. Does it lie far to the left or does it lie far to the right? Think about that. Does this equilibrium lie far to the left or far to the right? If it lies far to the left, these are the major species. If it lies far to the right, these are the major species. And how do you know whether it lies far to the left or right? Of course, it's the KB value. If this is a big number, far to the right. If this is a small number, like this, far to the left. Major species, ammonia. The ammonia is there most of the time. We wrote the reaction. What is the pH? Set up your ice table. I'm just going to write right over this. Initially, 0, 0. So, we're going to be going through some of these fast. It's the same process every time as far as doing the equilibrium constant expression stuff. Minus x, plus x, plus x, the change. How do we know it goes from right to left? We start with this, and we don't have any of this to begin with. At equilibrium. In typical form now, we can write this and write this quickly. This is for a weak base, but it is the exact same process that we have used for a weak acid. So this is Kb 1.8 times 10 to the minus fifth is equal to x squared all over 0.0750, number on the worksheet, minus x, which is equal to x squared all over 0.0750. In other words, I'm just automatically ignoring this from now on. Just going to do this a little bit more in case that's not coming through. So this number is equal to x squared over this. And if we solve it, we get a number that I believe is 0.00116. Does this number change 0.075? The answer is just a little bit. So if you plug this 0.00116 in here and resolve for the x squared term, you get 0.00115. Same pattern every time. Notice what we have. All of our coefficients are 1. This is just like working a weak acid problem. The weak base problem, we use a Kb instead of a Ka. And we still do the ice table, and we end up with this. Now, to get the answer, let's see, 0.00115. Now what I want to do is I want to take the negative log, or I want to, first we have this number, this is x. So what does x represent? X is the amount of ammonium ion we formed. It's also the amount of hydroxide. In other words, we now have hydroxide being produced to this degree. Now that we know the concentration of hydroxide at equilibrium, x, we can find the pH. So if I do the log of the negative log of this, I get a number 2.94. pOH is equal to 2.94. 11.06. The most common error that students make is you assume that X is hydrogen concentration, which is what you do have for weak acid problems, not for weak base problems. For weak base problems, X is hydroxide, and now it's a two-step conversion to get pH. I'm just going to do this calculation again to make sure I've done it right. Then let's see, times. 0, 0. Okay, now we do 0, 0, 7. While I'm doing this, you can do these calculations along with me. Okay, let's root. Where that came from. There we go. Okay. So I had done it correctly. Just wanted to make sure that I had these numbers right. So somewhere down the road in this video, as you're watching it, it's like, where did he get those numbers? Those are wrong, or not the numbers I get. Okay, at least these numbers I believe are correct. So the negative log of that, 2.94, and then, so again, remember this is POH, not pH. All right, here we go. Now what do we do with salt solutions? All right. Acids and bases. How have we been talking about acids and bases? We've been talking about acids and bases just with like HA being a weak acid and a base, which is a hydrogen ion acceptor. We've talked about them as neutral compounds. An acid, which we call HA, it could be a cation that gives away an H+. It could be a neutral compound, HA, that gives away a hydrogen ion. Or it could be an anion that gives away a hydrogen ion. They can all act as weak acids. And we treat those, if it's a weak acid, we treat it as a weak acid in solution with the standard reaction, the weak acid giving away a hydrogen ion. The same thing is true for a weak base. A weak base can be cation, neutral, or an anion. As long as it's accepting a hydrogen ion, it's going to be a weak base. So we have those two reactions for weak. That's it. And it's the same kind of calculation for the ice table. It's going to be K, Ka or Kb, equals x squared over a number, the original concentration. It's just that simple. And then you always want to check that to make sure that whatever x turns out to be, that it doesn't change that denominator of that initial concentration. Salts. Salts can be acids and bases. And so here are the questions. If you screenshot this or whatever, or write this down, pause the video, write it down. This would probably be a good thing to put in your notes. So you have a salt. How do you know it's a salt? Cation, anion, just like we've been naming all semester. You first ask yourself, is the salt soluble? You know the solubility rules. We've talked about that earlier in the semester. Then, is the cation from a strong or weak base? Is the anion from a strong or weak acid? So if both come from a strong base and a strong acid, then the pH will be neutral. If the cation is from a weak base and the anion, if the cation is from a weak base, the pH will be acidic. And if the anion is from a weak acid, the pH will be basic. Now, don't worry about these for a minute. These are really the key questions, and we'll talk about how to apply that in the next slide. All right, so we're not going to calculate the pHs here specifically. Well, we can, I guess, maybe we can. But here we have 3 different salts, and let's treat them individually. Remember the questions. Is the salt soluble? NaCl, is it soluble? Yes. In fact, all of these are going to be soluble because they fit the solubility rules. So all sodium salts are soluble, all ammonium salts are soluble, and of course, sodium again. So they're all soluble. Let's look at the first one. Na is the cation of NaOH, strong base. Cl minus, the anion of a strong acid. Strong base, strong acid, neutral. And what that means is this. Sodium hydroxide is a strong base because it totally separates in water, and the sodium doesn't want anything more to do with the water other than be surrounded by water molecules. By that I mean, sodium is not grabbing a hydrogen from a nearby water and holding onto it. Sodium ion has no affinity for hydrogen ions, for hydrogen from water at all, other than it wants to be soluble. Chloride comes from HCl. HCl is a strong acid because when you put HCl in water, it totally separates into its ions. Chloride wants no more of anything to do with hydrogen ion. So chloride runs off by itself. This comes from a strong base. This comes from a strong acid. In water, they are totally stable, happy, surrounded by water, and they don't feel the need to grab water and grab hydrogens and hold on to them in any way, shape, or form. This doesn't feel the need to grab hydrogens. This does not feel the need to grab hydroxide. When we come to NH4Cl, here we have chloride again, which we know does nothing, anion of a strong acid. Ammonium ion, on the other hand, is the conjugate base of ammonia. I'm sorry, the conjugate acid of ammonia, the weak base. Ammonia, the weak base, NH4 plus conjugate acid. So what do we do with this? Well, the first thing we do is get the board open. All right. Okay. We know that chloride does nothing, but we have ammonium ion, NH4 plus. About 2 or 3 weeks ago, there was a slide that I sent you, or that I posted, where it lists acids and bases in order from strongest to weakest. So the strongest acid has the weakest conjugate base. As acid strength goes down, in other words, as the anion holds tighter and tighter to the hydrogen, the conjugate base strength goes up, which means that in solution, the weaker the acid, the stronger its conjugate base, knowing that they are still both weak. And that's kind of a hard concept to get your mind around. So we know the chloride does nothing, but what about the ammonium? This is a weak acid. Just like NH3 is a weak base, NH4 plus is a weak acid. And it undergoes an interaction with water. Plus H3O. Because this can weakly donate a hydrogen ion to water, leaving you the conjugate base and forming hydronium ion. So this is what we have now in solution. This is a salt where one of those two, the cation or the anion, in this case the cation, is acting as a weak acid. If it is 0.1 molar, then we start with 0.1 molar NH4 plus. This is totally soluble, right? So if this is 0.10 molar soluble in ammonium chloride, because this is a soluble salt, and when salts dissolve, they totally separate. This is 0.1 molar in ammonium ion, 0.1 molar in chloride. So what happens next? We have a weak acid, and its conjugate base is NH3. This has a Kb. NH4 plus has a Ka. Whenever we have, and I keep coming back to the term conjugate acid-base pair, acid-base, conjugate acid-base pair. For a conjugate acid-base pair, the Ka times the Kb is equal to Kw, or Kw is the ionization constant of water. In your text, they derive this. They illustrate how you get this. Kw is 1.00 times 10 to the minus 14. And if you don't know that, you probably will because of working with problems like this. So in order to find out whether something is an acid or a base, in the back of books, I have an analytical chemistry textbook that I've used. And in the back, there is a table with about 12 pages of weak acids. And it lists the weak acids and Ka values. It doesn't list any Kb values, because if you have the base, you can always find the Kb from this simple equation. In other words, it's assumed that if Ka is known, you can know the Kb for its conjugate base. So in that table, you won't find a Kb for ammonia, but you will find a Ka for ammonium ion. So now that we have this reaction, this is a Ka, it's an acid. Remember, there's only two reactions for weak, acid, base. Here we have the acid form. The Ka for this, and so we know that Kb from the previous problem that we did is 1.8 times 10 to the minus fifth. The Ka is equal to Kw divided by Kb. And this number is equal to 5.56 or 5.6. Oh, we'll call it 5.6 times 10 to the minus 10. And then how do we fill this out? This is like any other acid-base problem. Minus x plus x plus x, so that at equilibrium, this number, Ka, is equal to x squared and I just ignore this x. Can we always ignore the x? No. But most of the time we can. And remember, the difference is if we look at these two numbers, if they're different by more than a factor of 10 to the third, more than a factor of 1,000, then you can always ignore x. And much like what we did with the first problem with ammonia, hey, if x is going to make a difference in this number, you solve for x from the x squared term, plug it in here, and then resolve it for x squared again. So let's say if this is 0.01, if x turns out to be 0.01, you plug it back in here, your denominator becomes 0.09, and you solve for the x squared term, and then you arrive very quickly at the correct value. All right, so this is it. And we end up with a number for x that is going to, let's see, use my calculator, 5.6 times 10 to the minus 10th times 0.1 and the square root of it. I get a number 7.48 times 10 to the minus 6, 10 to the minus 6. 7.48 times 10 to the minus 6. What is that? What does that mean? This number is x. X is the equilibrium concentration of hydrogen ion concentration. Remember, H3O plus and hydrogen ion are exactly the same thing. Hydronium ion, hydrogen ion, same thing. Yeah. So all I do is take the negative log of that, and my pH is 5.13. So what is the pH of a solution 0.1 molar in this? 5.13. With sodium nitrite, I can do the exact same thing. So by the way, before we go into there, ammonium chloride. This comes from a weak base. This comes from a strong acid. Weak base, strong acid, acidic. And it's acidic, pH here is less than 7. For sodium nitrite, it's the same thing. Strong base, weak acid. Strong base, weak acid. Now, when I say strong base, this comes from NaOH, strong base. This comes from HNO2, nitrous acid, a weak acid. Strong base, weak acid, basic. This will have a pH greater than 7. And just to set it up, because I haven't looked up the Ka value for nitrous acid, this is where you would go with it. It would look something like this. And sodium ion comes from a strong base. It sits in water, it doesn't react with it. Nitrite, however, the conjugate base of a weak acid, will react. So remember, for anything that's weak acid, its conjugate base is also weak. Weak base, its conjugate acid is also weak. You have to write the reaction according to what you have. So this is now going to take a hydrogen from water and become HNO2, and this is going to be left with OH. Nitrite acts as a weak base in water. Here's the equation for it. So the Kb is going to be Kw over Ka, whatever the Ka value is. And then if this is 0.1, x, you're going to have Ka is equal to Kw over Kb. I'm sorry, got this wrong. Kb, Kw over Ka, which will be some number. And this is going to be x squared all over 0.10. How do I know that? X, 0.1 minus x. We ignore the x in the denominator, solve for x, and we should be pretty close to the value that we're looking for. Now, remember that the x that you get is hydroxide concentration, not hydrogen ion concentration. So what I'd like you to do is on worksheet 14, I'd like you to try problem 4, because by now you should be able to set it up. In fact, what we'll do is we will set that up right here. Because it's the same thing we've been talking about, right? Take a look at problem 4 on worksheet 14. Using cyanide, HCN. And on worksheet 14, I'm trying to remember what the number is. I don't know if I have a copy to look it up. Let's see. Okay, so the pKa is 9.2, 9.31, 9.30. So just doing this, I'm getting 9.3, 9.2, 9.31. I'm going to use 9.30. Let's see. Doesn't seem right. Let's try 9.2. This is a little better. I want something around 6.3. I know it's in worksheet 14. 6.3 times 10 to the minus 10. So this is going to be over 6. Might be 6.28. I'm gonna. I don't remember exactly. Anyway, you've got worksheet 14 in front of you. Work this out. Solve this out, and then this is equal to x squared all over 0.10. It's technically 0.10 minus x. Solve for x. X is hydroxide concentration. From hydroxide, then POH, and then pH. All right. Oh, here it is, 6.2 times 10 to the minus 10. 6.2 times 10 to the minus 10. 6.2 times 10 minus 10. So anyway, calculate for 0.75. Oh, it's not 0.10. Okay, 0.75. We find Kb, the Kb of cyanide being the conjugate base of the weak acid hydrocyanic acid, HCN. Weak acid, its conjugate base is also weak. Ka is 6.2 times 10 to the minus 10. The Kb let's see. Divided by 1.6 times 10 to the minus 5. We solve for x squared. Let's just go ahead and finish this off. Let's see, 3.5 times 10 to the minus 3. .00348 is what I get, so we'll round that off here. And then, let's see, negative log of that is 2.46. 2.46. Is this the pH or the POH? 2.46. So remember that X is hydroxide concentration. So X is hydroxide concentration, therefore this is POH. And then the pH, 11.54. Right. Yep, there we go, 11.54. All right, basic. This is the Kb of cyanide. This is the Ka of HCN. And this is how those are related. You either have for weak, you either have an acid or you have a base. Okay. So let us take a look here at a high level overview. Rather than determine the pH, we will, maybe not thoroughly. Let's look at this. Let's look at the first one. Is this obvious or not? Determine the pH. What do we have? We have HNO3. Strong or weak? First question, strong or weak? HNO3, strong. That means that the hydrogen ion concentration is 0.1 and nitrate ion concentration is 0.1. Negative log of 0.1 is 1. So the pH of this solution is 1, and we haven't even had to do any real calculations with the calculator. Once you've identified the system, you know where to go and how to calculate pH. Strong acid, the concentration is the hydrogen ion concentration. Weak acid, now what do? Write the reaction. HNO2 plus water. Hydrogen's the only cation, it gives it away. Look up the Ka. So the Ka is equal to x squared over 0.1. Solve for x. X will be the hydrogen ion concentration. Find pH from that. High level overview. What do we have? Strong acid, weak acid. What about here? What will our pH be? Think about it for a moment. This is a base. Strong or weak? Do you have the pH already? Did you come up with 13, which is the correct answer? The hydroxide concentration is 0.10 molar. 0.100 molar. If hydroxide is 0.100 molar, negative log of that is 1, the POH is 1, the pH is 13, because pH plus POH equals 14. Remember that diagram where hydrogen ion concentration, hydroxide, pH, pOH. You've got to know that. You've really got to know that because doing those interconversions has to be automatic by now. Finally, we have ammonia. How do we find the pH here? This is just like problem 3 on worksheet 14. We did at the beginning of this session. Ammonia plus water. Take a look at that. Now, the Kb for ammonia is equal to x squared over 0.1. The Kb for ammonia, 1.8 times 10 minus 5th, is equal to x squared over 0.1 because that's what we have in equilibrium. It's the same format because for acid-base chemistry, the coefficients are always 1. All right, so that's our survey, our overview of how you would go about solving them. So where we're going to end today is just a few comments about acid-base titrations. I know that we're doing acid-base titration in lab this week, and the reason we do titrations is to actually calculate to quantify how much acid or base is in something. So what we do is we take, let's say for example, we take a base like a strong base like NaOH, almost always used as the base, as the titrant, as what we use in titrations. Strong base because the concentration of OH is 0.100 molar. Strong base concentration of OH is 0.100 molar. Usually we will use a known concentration and a volume to determine how many moles of OH are being added in a titration. The goal is to find the point where moles of acid is equal to moles of base. Now what we're going to be doing here is we'll be calculating, this is actually our next worksheet, which will start here on Wednesday. We'll be working through this worksheet on calculating strong acid, strong base titration. The one thing that I hope you get out of what we've talked about today is looking at a problem and saying, what do we have? What are we starting with? For an acid-based problem, there are really 4 conditions. We have strong acid or strong base, one of those 2. Strong or weak acid or weak base, one of those 2. Once you recognize what you have, then the calculations follow. If it's a strong acid or strong base, pH is directly related to the concentration of hydrogen ion or hydroxide. If it's weak, then you have either a weak acid problem or a weak base problem. And it's important to recognize that conjugate acid-base relationship. Okay, so here's where we're going to start on Wednesday, and I think I'm going to stop here for the Zoom recording.